Hey there, just as a reminder, you might find that listening to me narrate can be helpful the first time you go through this, but if you want to be able to go through at your own pace, or if you want to just be able to look at some specific slides, you can either download this PowerPoint from Quick Schools, and I'll have a couple of options because some of you might want all the animation, or you might say, hey, no, I don't want any of the animation. I just want to see like the notes and the examples. All that will be available on Quick Schools. And so if you don't find watching this on video format to be that useful, you can download the PowerPoint or whatever you want to do with that. If you're wondering why the Space Needle is going by, the design of the Space Needle, the legs are all hyperbolas, right? So in engineering and architecture, this shape will actually come into play quite a bit. And for this first lesson on the hyperbola, we're going to have them centered at the origin. And then after we get through this lesson, next class session will be like, okay, what happens if the hyperbola is not centered at the origin? Now, in some ways, this is very similar to the ellipse. You'll notice that the x squared is over a number squared, the y squared is over a number squared, and it's equal to 1. So just like the ellipse, you've got a couple of fractions, and they're equal to 1. Big difference, you'll notice, though, is that there is a subtraction symbol instead of addition. Right? It's not x squared over a number plus y squared over a number, right? We've got subtraction, or it could even be y squared over a number minus x squared over a number. Now, unlike the ellipse, right? The ellipse, we also had to try to figure out, well, gee, which number is going to be the a squared and which number is going to be the b squared. And then we said, hey, well, the larger number gets to be the a squared. Well, since one of those fractions is positive and one of them is negative, the positive fraction is always going to have the larger value, right? Any positive number is greater than any negative number. So notice that whichever variable comes first, whether it's the x squared or the y squared, it is always over the a squared, right? So the a squared will always go with the vertices. So if we have x squared over a squared to start the equation, the vertices are going to be going left and right in the horizontal direction for x. If we start out with y squared over a squared, the vertices will be going up and down vertically in the direction of y. And then the other twist with the ellipse, if we had subtracting to figure out the value of c, notice here we're going to do adding to find the value of c. So I want to do one example where we start out with the x squared over a squared, and then I'll do one example where we start out with the y squared over a squared. So I've got x squared over 16 minus y squared over 9 equals 1. If you have a printer at home and you actually want to print this off and actually do it on paper, that's available at Quick Schools. So I'm saying, okay, I've got to have x squared over a squared, and then I've got to have minus y squared over b squared equals 1. So I got to think of that 16 as actually being 4 squared. I can think of that 9 as being 3 squared. So for the vertices, I'm like, aha! It starts out with x squared, so the vertices will be going left and right. I see a 4 squared, so I know I got to go 4 units. So the vertices will be at 4, 0 and negative 4, 0. And I can put those dots on my graph paper. So I've got a vertex at each of those 2 points, right? 2 vertices. Each one is a vertex. Now again, to figure out the value of C for the focus, instead of subtraction, I'm doing addition. So I'll do 16 plus 9 inside that square root symbol. I end up with a value of 5 when I take the square root. And notice that the foci are further away from the origin than the vertices. Right? The vertex might have only been 4 units away from 0, 0, but the focus is 5 units away from 0, 0. Now, we have to figure out the asymptotes. As a reminder, the asymptote is a straight line that my curve will get closer and closer and closer and closer to. Now, where did that crazy rectangle just come from? Well, underneath the y squared, I had 3 squared. So notice I went up 3 units and down 3 units. So that rectangle from the origin goes 4 units to the left and 4 units to the right because of the 4 squared. It goes 3 units up and 3 units down because of the 3 squared. The diagonals of that rectangle are my asymptotes. So, for the purpose of the hyperbola, I know it has to go through the vertex. Just like a parabola, it kind of wraps around the focus. But instead of doing like a U shape the way a parabola would, it kind of almost makes out a rounded V shape. Right, because if I really zoomed out, those curves would almost look like a V because they're approaching those straight lines instead of curving forever. But of course, it's not really a V because it is rounded at the vertex. And notice I was able to figure out the equations of the asymptotes, right, in the format of y equals mx plus b. The slope of one of the asymptotes is positive 3/4. The slope of the other asymptote is negative 3/4. And of course, since I go through the origin, in each case, b, the y-intercept, is 0. Okay, so let's take a look at an example where the y squared is positive. Uh-oh, I don't see equals 1. I've got 4y squared minus 49x squared equals 196. I really need to have a 1 on the right-hand side of that equation. So to accomplish this, I'll need to divide everything by 196. Now, if I take 196 and divide it by 4, I'll get 49. So it's like, oh, I'm lucky. 4 times 49 makes that 196. So when I reduce those fractions, 4 over 196 is 1 over 49. 49 over 196 is 1/4. So I know that 49 is 7 squared. 4 is 2 squared. And so for the vertices, I'm like, okay, well, this time the vertices would be going up and down because the y squared is positive. Right? When the x squared is positive, the vertices are left and right. When the y squared is positive, then I've got to go up and down. So one vertex will be at 0, 7. The other vertex will be at 0, -7. Now, to figure out the foci, again, I'll do addition inside that square root symbol. So I've got to do 49 plus 4. That, of course, will get me 53. And then square root of 53, what can I do with that? Well, 53 is a prime number. I cannot think of any way of simplifying square root of 53. Now, because I've got to put dots on my graph, though, I might grab a calculator and say, hey, calculator, what's the square root of 53? But if I want the exact answers, one focus is at 0, comma square root of 53. The other focus is at 0, comma negative square root of 53. So the foci are really close to the vertices. Right? From 7 to 7.28. On my graph, they're going to look like they're almost on top of each other. For the asymptotes, because underneath the x squared is a 4, and I know 4 is really 2 squared, I will go 2 units left, 2 units right. And there is that rectangle. Again, the rectangle's not part of the hyperbola, but the rectangle helps me draw the asymptotes. The asymptotes are the diagonal lines that go through that rectangle. They go through the corners of that rectangle. So it looks like one of the asymptotes is y equals 7 halves x, right? It goes up 7, right 2, up 7, right 2, up 7, right 2, right? That's the slope. The other asymptote has a slope that goes down 7, right 2, down 7, right 2. So that slope is negative 7 over 2. And of course, because I've got the hyperbola centered at the origin, there's no y-intercept to show because the y-intercept is 0. I don't need to put plus 0. And so again, when I try to draw the hyperbola, I can use those asymptotes as a guideline. And so I'll kind of draw a line that's kind of straight, kind of close to the asymptote, but then it'll curve as it goes through the vertex and then go out approaching that other straight line. So you might even want to think about this as it's kind of like it's two different parabolas on the same picture, right? The way a parabola would wrap around the focus as it goes through the vertex. Big difference, though, is that the parabola, if we really zoomed out, would look like a U shape, where this hyperbola, if we really zoomed out, it would look like a couple of V's, because they become much straighter. They don't keep curving forever the way a parabola does. Again, our good old friend, the Space Needle. If you look at the legs, you've got some hyperbolas going on there. Probably not as prevalent as we'd see with parabolas. Right, suspension bridges are all over the place, and those cables are parabolas. Ellipses are also quite common in architecture. Hyperbola, not quite so much, but they do show up. And so there's a worksheet that you can download, or if you want, you can just take a look at the worksheet online and then just copy the equations down on paper. And if you want to just work with pencil and paper, please email me with any questions. But otherwise, best wishes. I'd much rather be doing this in person on campus, and at some point in time that will resume. But right now we're just going to try to make the best of this situation as we can.